For problem number 52, Wayne Gretzky, the great one, passes a puck across the surface of the ice in such a way that it gets only halfway to his teammate. Okay? He wants it to go some distance d, but it only goes half that far. So, over a distance d, the puck loses all of its kinetic energy. Everybody okay with that? All right, because the work done by friction, a non-conservative force, is going to be equal to negative force of friction times the distance, right? I'm going to use just one little f instead of big F subscript, all right? So negative FD. Okay, so
friction is the entire force times distance.
The work done by friction will be the force times distance, because let's take a look. Well, that's a good question, Katie, because we have some velocity, some displacement rather, right? And then we've got the force of friction acting in the opposite direction. So the angle between them is what? 180 degrees, right? Cosine of 180 is equal to -1, right? So if we want to be like really mathy here, we've got force of friction as a vector. Oh, how did that happen? All right, I don't know. It doesn't erase. So now we're in big trouble. All right, so we've got, what was I saying? All right, we've got force of friction as a vector dot the displacement as a vector is equal to magnitude of F times magnitude of D times the cosine phi, the angle between them. Okay, since we know that's -1 right here, it's just going to be negative FD. All right, so it says specifically in the problem that the force is going to remain the same. The magnitude of the force isn't going to change. Why would it? The coefficient of friction between the puck and the ice is going to stay the same. The weight of the puck, which is the normal force is going to stay the same. So that the magnitude of that force is going to be the same. So the only thing that's going to determine how much work gets done by friction is how far it slides. Does that make sense? All right, so is energy conserved? How do you know?
Always is.
No, well, no, it's not. It's not conserved within the system. Why? Because a non-conservative force, friction, acts on it. Okay. So another way of looking at this is gravity acting on the puck? Let's take a look at a free body diagram for the puck. Right? Normal force. Is normal force going to do any work as the puck slides in this direction? Why? It's perpendicular, and therefore it does no work. All right? What other forces are acting on it? Well, we got the weight.
We count the external force that would hit the puck.
No, once it's sliding. Okay? Once it's sliding, as it's sliding, the net force acting on it is friction, isn't it? Okay? So even if we write this in that conservation of energy kind of way, we could still, that'll give us a starting point. It's unnecessarily complex, or we don't really need to go back that far, but just to give ourselves a starting point, let's do that. Let's say that mgh, actually, let's do it the other way. Remember we do the delta K is equal to negative delta U. We can only write that if energy is conserved. So scratch that out too. All right. K plus UG plus work done by non-conservative forces is going to be equal to, these are the knots, is going to be equal to K final plus UG final. All right, what is all that? That's a bunch of symbols. What does that mean? This is our initial kinetic energy. This is our initial potential energy. If we add the work done by non-conservative forces, we will get the sum of the kinetic and potential energies at the end, or at any point thereafter, right? After this much work is done. Got that? Great. It's going to be a great video. All right. So, yesterday we did the baseball bat problem. Remember that one?
Yeah.
Work was done by a non-conservative force. What was it? The baseball bat. Remember we had a certain amount of potential energy which we took to be 0. We took this to be 0. We had a kinetic energy based on the speed of the pitch. Then work was done by the bat, and then this was our energy budget thereafter, when all that was working was conservative force of gravity as it was flying through the air. Okay? Just remembering that. So now we have exactly the same thing going on here, except what is the change in potential energy going to be as it slides across a level surface? Yeah, if we take the surface of the ice to be 0, this is 0 right from the beginning, and this is 0 right from the beginning. So all we're really saying is that initial kinetic energy plus the work done by non-conservative forces is going to be equal to the final kinetic energy. And in our case, what's the final kinetic energy? 0. Why is it 0? Because it comes to rest, right? The puck has come to rest. So we could say that K naught plus, that's our initial kinetic energy, 1/2 mv squared, plus the work done, I'll go ahead and put an F in there because that's the non-conservative force, friction, is going to be equal to 0. So the work done by friction has got to be equal to, well, let me do it this way actually. Kinetic energy is going to be equal to the negative of the work done by friction. What does that mean? Kinetic energy is going to be equal to the work done by friction. If it comes to rest, then the kinetic energy at the beginning has to be equal to the work done by friction. Does that make sense? All right. So how do we define work done by friction? Bless you. So that means that the kinetic energy has got to be equal to the negative of the work done by friction, which is just negative Fd, friction force, times the distance that it slides. Another way of saying that is, the whole question is about the distance that it slides. So why don't we take this in terms of distance? Can't we say that, so these negatives are going to cancel each other out, right? Can't we say that the distance it slides is going to be equal to the kinetic energy that it's initially given divided by the frictional force? Pretty easy. And what is kinetic energy going to be equal to? 1/2 mv naught squared over friction, or if you prefer, you could say the distance that it slides, no matter what, the distance that it slides is going to be equal to the mass of the puck times v naught squared divided by 2f. Okay? Now, just for fun, we don't need to do this. I want to just show you something for fun. Because when I was writing this, I was like, I don't think that the mass matters in this. It looks like it matters, but why doesn't it matter? Because the friction force is going to be proportional to mass as well. Good. Okay? So this is not really part of this problem. I just wanted to see if you had some intuitive sense that the mass might not matter. You were correct in your thinking. So now, this is true no matter what. This is a generalized expression. We haven't put in our original information or what we're trying to do or anything like that, right? So, in our initial case, the velocity that we gave it, v naught, was equal to 1.7 meters per second, correct? And this resulted in a distance of d. What we want is we want some other v naught that's going to give us 2d. Can you see that? So what we're saying is the ratio of 2d to d will give us a ratio of v naught prime to v naught. This is the way we've been solving problems like this all year. So we want the new distance, okay, we'll call this d prime, okay? So if we say d prime over d, we want to be equal to 2. We want it to go twice as far as it did. And to do that, we have to say d prime is going to be equal to m v naught prime squared over 2f, right? Divided by m v naught squared over 2f. You guys understand where that comes from? In general, the distance that we go is going to be equal to m v naught squared over 2f. We want that ratio of our new distance over our old distance to be 2. So how are we going to compare how our v naught prime, how is that going to compare to v naught? And remember why we set things up as ratios? What does it do for us? It allows us to cancel out a bunch of junk. The 2F's cancel out. What else cancels out? The mass. So all we really are saying here, in the long run, in the final analysis, we are saying that V naught prime over, let's do it the easy way, V naught prime, nope, V naught prime squared over V naught squared is equal to 2. I was just going to put them together and square the whole fraction, but we have to separate them again anyway. That's why I backed up. So what are we solving for? All right, so V naught prime is equal to the square root of 2 V naught squared. Another way of saying that, simplifying, is V naught prime is equal to root 2 times V naught. We just take V naught squared out. And this is what we said all the way back at the beginning. Got an intuitive sense because of the change in energy. We had to have twice as much energy when the puck left the stick for the second case, for it to go twice as far as it initially did. So now all I have to do is multiply. So V naught prime is equal to root 2 times 1.7 meters per second, which we already established is 2.4 meters per second. All right? So that is a challenging problem. It's a challenging problem, no doubt about it. What do? We figured out how far it slid. We got the distance that the object would slide as a function of the work done by friction. Because friction is going to do negative work on it, reduce its speed from some initial value to 0. Because the initial value, or the final value, is 0, we know that the work done must have been equal to the initial kinetic energy. So we set those equal to each other. We figured out here, along here, we knew that there was no change in potential energy. So we said that the kinetic energy had to be equal to the negative of the work done. Once those were set equal to each other, we could get them in terms of distance and the frictional force. Okay? Final result, 2.4 meters per second.